In this video, we'll be talking about one last way that we can calculate the enthalpy change for a chemical reaction based on pre-existing data. So this time we're going to be using what's known as bond dissociation enthalpy, or sometimes bond dissociation energy, commonly abbreviated BDE. So what this is the enthalpy change when a bond is broken symmetrically. So what I mean by that is that if we're talking mostly about covalent bonds here, so a covalent bond is a pair of shared electrons. If the bond is broken symmetrically, one electron goes to each atom. If a bond is broken asymmetrically, both electrons go to one atom and the other one gets none. So bond dissociation enthalpy is specifically talking about symmetrically breaking a bond. How much energy does that take? Meaning that a one electron goes to each atom. So the simplest example would be if we think about a molecule of H2. There are two electrons in that molecule. They're shared between the two hydrogen atoms. When this bond breaks symmetrically, one electron goes to each of the two atoms. So the delta H for this reaction would be the bond dissociation energy for a hydrogen-hydrogen bond. So this is the type of reaction that we're thinking about when we're talking about bond dissociation enthalpies. So BDE values are always expressed as a positive. Because we're defining bond dissociation enthalpy as the energy required to pull your atoms apart. Breaking bonds is always endothermic. It requires an input of energy. Which is a really common misconception, actually, in chemistry. Somewhere in your science past, someone has probably said the phrase to you, energy is stored in chemical bonds. I hate this phrase because it conjures up an image of a bond as like an energy storage container, that you put energy into it, and if you break it out, the energy flies free, but that is exactly the opposite of how you want to think about it. Bonds form because atoms are attracted to one another. Atoms are like magnets, that they're attracted to one another, and that's why they connect. So if you want to separate two things that are attracted to one another, you've got to pull. You have to put energy in order to pull those two atoms apart. Conversely, when new bonds form, energy is actually released. That those two atoms are attracted to one another, they connect, thereby lowering their energy. That energy has to go somewhere. It's released to the surroundings. So breaking bonds is endothermic because your atoms are attracted to one another, and you have to put in energy to pull them apart. Forming bonds is exothermic. And would be described by the opposite of the bond dissociation energy. breaking a bond, forming a bond are opposite processes, so the same amount of energy is going to be transferred, just in the opposite direction. So all chemical reactions can be thought of as breaking and forming bonds. Specifically, that we are breaking apart our reactants, so we're breaking the bonds in our reactants, and we are shuffling atoms around and creating new bonds in our products. So we're forming new bonds in the products. So all chemical reactions can be thought of as breaking up the bonds in the reactants, which requires an input of energy and then forming the bonds in the products, which releases energy. So we can look up bond dissociation energy values for just about any type of bond we want. It's pretty well established. So BDE values can be looked up by the type of bond. But one thing to keep in mind with using bond dissociation enthalpy is the value that you find is not specific to one particular compound. So the value reported is an average value for many, many different compounds containing that same type of bond. And bond strength does vary a bit from compound to compound. So what that means is that any calculations you do with bond dissociation energies are approximations. They're not an exact calculation for your particular reaction or your particular compounds, but they're a pretty good estimate. So delta H values calculated using bond dissociation energy are only approximate. So you may wonder, why do we want an approximation when we have these other ways, using Hess's law and using heats of formation, when we can calculate delta H exactly? And one of the biggest reasons is really that those other two methods require the compounds that you're using to be well studied already, that in order for the heat of formation of a compound to be known, it needs to have been created and studied previously. And sometimes in science, you're working with something brand new to humanity. You may be creating a brand new compound that no one has ever made before. It's not as exciting as it sounds. But if no one's ever created this compound before, there won't be a heat of formation for it. There won't be delta H's known for any other reactions involving it. So we can't use those other methods. But to use bond energy, all you need to know is the structure. So if you know what you made, or if you know what you think you made anyways, you can use the structure and the bonds involved in that structure to get a really good approximation of the delta H based on bond enthalpy values. So in a lot of cases, an approximation is a good enough starting point. If all we want to know is, is this extremely exothermic? Do I need to worry about the energy being released? This is a good way to get an approximation. So Similarly to heat of formation, we have kind of an equation that we can use for this. So delta H, when we're using bond dissociation energies, we're going to take the sum of the bond dissociation energies for all of the bonds that we break, and we're going to subtract the sum of the bond dissociation energies for all of the bonds that we formed. So in general, we are breaking up our reactants and we are forming products. So we're breaking bonds on the reactant side, we're forming bonds on the product side. So this one is backwards. If you're thinking about it in terms of reactants and products, it's different from the heat of formation one. And the reason for that is coming back to the fact that breaking bonds is endothermic, which means that we'll use the BDE values as they are given, which is always positive. But forming bonds is exothermic, which is why we're subtracting, which is why that subtraction, that negative sign, is now going to apply to our entire product side, all of the bonds that we formed, because all of those released energy when they formed. So if we want to calculate delta H using bond energies, we just need to know the structure, the actual full structure of all of our reactants and products. Note that I will not be asking you to draw Lewis structures at this point. And we need to know the bond energy or the bond enthalpy for each of the type of bonds that's involved. So we'll want to keep in mind that this is given per mole. So if there's more than one of the same type of bond in a compound, we're going to have to multiply. If there's a coefficient out in front, we're also going to have to multiply to figure out how many total bonds of that type are present in our compound. But why don't you pause here and try to solve this problem on your own. So for this one, we're going to want to identify the different types of bonds that we have present in our reactants and products. So we have carbon-hydrogen bonds present in acetylene. We also have a carbon-carbon triple bond present in acetylene. We've got an oxygen-oxygen double bond in O2. We have carbon-oxygen double bonds in carbon dioxide, and we have oxygen-hydrogen single bonds in water. So once we've identified the different types of bonds and that we have all of the data that we need here, we can work on essentially just plugging in to this formula. So we want to start with all of the bonds that we're breaking, which is going to be all of the bonds in our formula. In our reactant side, sorry, all of the bonds on the reactant side that we're going to be breaking up. So to find our delta H, we're going to have, we have 2 moles of acetylene, and each acetylene molecule contains 2 CH bonds. So we have a grand total of 4 CH bonds. So we're going to do 4 times the CH bond energy. We have this coefficient of 2 also applies to the carbon-carbon triple bond, but there's only 1 per molecule, giving us a total of 2 carbon-carbon triple bonds. We also have 5 oxygen-oxygen double bonds. And that will take care of the reactant side of things. From that, we're going to subtract. On the product side, we have 4 moles of CO2. Each molecule contains 2 carbon-oxygen double bonds for a total of 8 carbon-oxygen double bonds. And then we have 2 moles of water, each of which contains 2 oxygen-hydrogen single bonds for a total of 4. So once we've kind of taken inventory of what do we have, so reminder, this was that we have 2 moles and we have 2 bonds in there in each molecule. So 2 times 2 is giving us our 4 CH bonds in total. This coefficient of 2 times the 1 C triple bond C gives us a total of 2 of that type of bond. We have 5 oxygen-oxygen double bonds. We have 4 moles of CO2, 2 bonds in each. 4 times 2 gives us 8 in total. And then we have 2 moles of water. Each one contains 2 OH bonds, 2 times 2 for a total of 4. So at this point, we can just plug in numbers from our table. So we'll have 4 times the CH value is 413, plus 2 times the carbon triple bond is 839, plus 5 times oxygen double bond is 495. From that, we will subtract 8 times 799 plus 4 times 463. So be consistent with my colors. When we do that calculation out, we find negative 2439 kilojoules per mole. So we did actually this exact same calculation using heats of formation in my previous video, and we got a slightly different answer. We got a value of, hold on, let me look. Negative 2511. So slightly different value calculated here, but remember, bond energies are approximate. So close enough that we can see this is pretty darn exothermic. In both cases, the heat of formation value would be more correct, would be more exact, but this is still telling us the information we need to know from this type of calculation. So it's still a useful approximation, but it's not quite as exact as heats of formation or Hess's law.